couple things I want to talk about to sort of keep going on things. One of them is these spectral techniques with filtering. Okay? What does filtering mean? So far we've learned how to basically, right, take these problems and we know how to implement spectral techniques now. And the spectral techniques we've implemented so far are FFT and the Cheb method. And the last thing I want to cover with you about these spectral techniques is, okay, so next lecture we'll go into the detail of this Cheb matrix on Wednesday. But there's one other issue that I want you to be familiar with because it's very important for speed. So let's go back to the idea of numerical stiffness. We've already, okay, STI. We've already introduced this concept. The idea here was if you have a problem with the high derivatives, right, and you start to discretize, if you remember, now your CFL, for instance, in this case here, looks like this. Now that delta x to the fourth on the bottom kills you, right? Because what it's really saying is if I want to get a little bit of better accuracy and keep my CFL condition constant, then if I cut this in half, right, and take delta x in half, then I get a factor of 16 on the bottom. So I have to take 16 times smaller time steps, okay? And remember, I doubled the number of points, so it takes me twice as long. So I have 32 times slower code, okay? So the higher the derivative, the more costly it is just to do something like double my accuracy. You double the accuracy, you're paying a high price for it, okay? That's that concept of numerical stiffness. Now, how it plays out in terms of spectral methods is that you can say, okay, let's go ahead and take this problem and let's Fourier transform it. So if you Fourier transform it in x, you get ut is equal to minus 4 derivatives gives you ik to the fourth. I to the fourth is 1. K to the fourth is k to the fourth. All right. There you go. Get this. Pretty simple. You say, oh, I got an ODE to solve. Okay. Where does numerical stiffness come in here? Well, let's take a look at this thing. So now you're going to take this thing here, and you're going to say, for instance, let's break this up into 128 Fourier modes. So if you say, I'm going to solve this thing, put it on a grid with 128 points, then my k values basically are going from negative 64 to 64. That's what happens now. And remember, you know this because if you remember, your k vector goes from 2 pi over L, remember that, times, and then you get from 1 to n over 2 minus 1 and minus n over 2 to negative 1. That's kind of how it looks in MATLAB, right? So up to 64. All right, so you have here k to the 4, and your biggest value of k is 64. So what is 64 to the fourth power? Here it is. I'm sure some of you worked it out in your head already. Right there. It is a number that's fairly big, right? It's like 10 to the 7. All right. 10 to the 7. Big deal. Well, here's the big deal about it. Out there on those Fourier modes, even if my solution is pretty small, let's say my Fourier number is 10 to the 6, minus 6 or something like that. 10 to minus 6 is pretty small, but now I'm multiplying it by this number, 10 to the 7. Okay? It's no longer small. This number is huge. It gets worse because 128 Fourier modes is not that much. What if I were to use 1024? Okay? 1024, yeah. 1024, 512. 512 to the fourth power. This gives you a number So this gives you k to the 4, which is a number like 10 to the 10. Okay, so your high frequencies way out there that are like almost 0. Well, almost 0. You're multiplying those numbers by 10 to the 10. Okay? So that's the problem with numerical stiffness. And by the way, the smallest any number is going to be is 10 to the minus 16. And now you're multiplying by huge numbers. This makes your code take much smaller delta t's. That is the cost you have to pay. Okay? All right, so that is the problem with numerical stiffness. So we want to try to figure out a way around this, or try to figure out if there's a way we can handle that term. Now, this is actually a fairly simple problem to solve, right? I mean, I could numerically solve it, or you could write down an exact solution, right? So it's something like some initial condition e to the minus, right? I wrote down the exact solution. So I'm doing all this work trying to get this thing to step forward like that exact solution when I already have it. Okay? So I'm paying a high price for it. So what we want to do is start thinking about this and trying to figure out, is there a way to get around this issue? Okay? So this is where the filtering idea comes in. And we want to consider, generically, not something quite as easy as what we have there, but something a little more sophisticated. LU times NU. LU is the linear part, linear, and has its derivative term. So for instance, the L might have the fourth derivative terms and things like this. We want to figure out, how do I take advantage of this? So we're going to have to do a little aside here, okay, for a moment, into how to solve differential equations. Okay, so I want to talk a little bit about, to come back to this problem, I want to solve the following first order linear equation. And we're going to talk about the method for solving this equation here. By the way, I haven't taught it for a long time, a differential equations course. And that's like day one. Day one. You start here and you say, how would you solve something like this? Okay? So day one, you start looking at this thing, and you start saying, well, what is the technique for doing something like this? And the way you typically do it, we're going to do it like, so I'd spend 50 minutes on it, but here we're going to do 10. The way I do it is I say, I'm going to multiply this equation by some function, mu. Okay? Mu of t. That's allowed, right? Everybody agrees I can make up a mu and I can do that? Okay? So I tell people in that class that I can do that. It's my board, my function mu. Do what I want. Okay. Sorry. Probably the people at home got this. Okay. All right. On the microphone. All right. So now, what do I want to do? I can make this up to be anything I want, right? This function mu. Mu is not going to be 0. Because it won't give me anything. But what I want to do is I want to make up a function mu so that what? So that I can actually write this whole left-hand side as, if you look at this thing, it's almost like it's a derivative of something. So in other words, if I had a function a of t times y of t, in fact, I'm not going to call it a of t. I'm going to call it mu of t here. Just take these two functions, multiply together, and just take the time derivative of this. Chain rule it. Or derivative first, or product rule it, not chain rule it. You know, take the derivative I got. Well, it's the first time derivative second. First, okay, so you get something like this. You get mu of t times dy dt plus, then you have d mu dt times y. Right? Simple. Now, here's the observation I want to make. Mu dy dt. Hey, isn't that what I got right there? So that's good. I'm going to do a little Charlie Brown squiggle on there. These two match up. This is du mu dt y. This is pt mu y. So I have a y in both places. And these would be exactly the same if du mu dt was equal to this p of t mu. Now, why would I want to do this, by the way? Because notice, if that were true, then this whole left side is just the derivative of something. You know what I love to integrate besides 0? The derivative of something. Because all I have to do is erase that dy dt. You should love that too. Okay? Because there's nothing like just undoing a differentiation with an integral. Or undoing, whatever, doing it backwards too. Okay? So this is really handy. And so I'm going to say, let's just make those equal. I get to pick mu. We already agreed about that, right? We already agreed on it. I get to pick it. We agreed when we first started. I made sure you agreed, so it's now legally binding. I get to pick mu. So I'm going to pick mu so that that's true. So I pick, start here. I'm going to pick d mu dt equals p of t mu. And if I do that, then that equation becomes d dt mu times y is equal to mu g. I can integrate both sides now. Right? So if I integrate this side, I get mu y is equal to mu g, and there's an integral there, dt, plus some arbitrary constant. And then that lets me write down what y is. Let me do it up here so everybody can see it. Y of t is equal to the integral of mu times g dt plus some constant all over mu. And we put that in a box in any good differential equations book. We'll have that in a box or in a shaded region or something. It is your highlighted formula. Okay? And that's how you get your solution. What we did was use this method of integrating factor. What we said is, look, if I can basically figure out a way to make this left side the derivative of something, then I can easily integrate it. Okay? And my mu then plays the role of an integrating factor. I multiply by this mu such that this left-hand side is the derivative of something. I can integrate it up. Okay? So that's how you do this. And it turns out it's not so hard to write down, of course, the solution to this d mu dy dt here. And let me do it here for you. So in fact, mu. What's that?
P is arbitrary.
P is arbitrary. And you can actually write down the solution of this as just e to the p of t dt. There's a simple way to get it, but let me just tell you what it is. That's your integrating factor. It's p of t. You integrate it, exponentiate it, put it in here, got your formula. Okay. This is how you solve first-order linear differential equations. And you have a formula, no matter what p of t is, no matter what g of t is. If you have a linear first-order differential equation, you can always solve it. You have analytic solutions. Okay? Okay, so how does this play a role for us today? Well, we're kind of make use of this here in this equation. In particular, I made the following comment. Let's come back over to here. When you have this fourth derivative term, the thing that's killing you is this numerical stiffness. The thing that's killing you is this k to the 4th. You're trying to find this exact solution, and you're just numerically solving, and it's uxxxxx kills you. But you already know the exact solution. Why not make use of it? And here, you'd say, well, if I know that, then I don't have to do any of this. Just, boom, there it is. I'm done. I got around my numerical stiffness because I know the answer. Well, so how could we take that advantage of that kind of thinking in this equation over here? What we're going to do is we're going to do a filtering method. We're going to, let's say, take a look at this thing here and just Fourier transform it. Okay? So we Fourier transform it. You get Fourier transform of some linear operator is just some function. Let's call it, actually I want to call it alpha of k, u hat, plus this nonlinear term. Now, by the way, whenever you have nonlinear terms, you always just have problems. Okay? So let's not deceive ourselves. Nonlinearity creates problems for you. Okay? And you just have to say, evaluate it, and Fourier transform it, and that's what you got to do. Okay? However, suppose that my stiffness is all coming from this term here. If it weren't for this, I'd know how to solve it. This is easy to solve. Boom. I do that. And in fact, let's pretend for a minute that there wasn't even there. If you just had this here, then your solution is just simply, oh, that's easy. Just e to the alpha k t. Solved it for exactly.